Hello everyone. Today I am here to discuss one more important data structure called B tree. B tree is one of the important data structure we have studied in both data structure as a subject and in design analysis of algorithm. This lecture is mainly concerned with the numerically aspect of B tree, like different operation, insertion and deletion. I'm just coming to it after giving introduction of this B tree. B tree data structure is a search tree data structure, means it is based on search property. Without going into too much detail into definition part, that is covered in another lecture. Today I am interested in discussing the practically insertion of different keys in an empty B tree. So first I am introducing B tree. B tree is one type of search tree in which more than one keys are stored in a node, and for putting keys there are certain rules. I'm just pinpointing the rules here. I'm coming to rules here. As far as we have seen a binary search tree like this one, 25, 20, 35. That means in this binary search tree there are three nodes. The root node having key value 25, the left child is having the key value of 20 and the right child key value is 35, maintaining the search property. Due to this single key in root node, we can attach only two children. The left subtree contains all key values less than 25 and the right subtree contains all keys value greater than 25. So for more practical use, the number of keys are increased, just like this one. Suppose this is one node and we have inserted two keys like 20 and 35. This cell represents more than one information. The first one is this node has two key values, means this node structure contain storage for two key values. Suppose these two key values are integer, we can take any key value. अगर ये दोनों integer हैं, तो the node structure will contain two fields for storing integer 1, integer 2, along with other field also like pointers. This will explain in the another lecture where implementation is concerned. Now I am coming to this. By principle of search property, the leftmost subtree hanging here will contain all the keys less than 20. The subtree in between 20 and 35 will contain key values greater than equals to 20 and less than equals to 35. And similarly, the key value after this key value 35, the right subtree hanging will contain all the key values greater than 35. Using this basic property, we can increase the number of keys in a B tree, and this will help to maintain the height. As we all know, the time complexity of almost all of the algorithm or operation in tree data structure depends upon the height of the tree. Increasing the number of keys will reduce the height of B tree, and that in subsequent will reduce the time complexity or time taken in any operation of the tree. Now I am coming to the practical part. The question given in university exam is like this. You have given some key values like 99, 22, 24, 48, and there is a question statement. Insert these key values in the same sequence given here in an empty B tree. A B tree having no key values, empty B tree. Inserting keys one by one will grow the B tree. So I am coming to that. The question may contain two different phrases. The first one is order and the second one is degree. Students generally confuse between these two. These two phrases are related with B tree for constructing B tree, and these two phrases are very important. Order of B tree defines maximum number of children. Usually, in general speaking, order is taken as the maximum number of children. This maximum word is written or not. Generally, in common statement, we ignore the word maximum. But order itself reflects it is maximum. There is no certain rule, but it is customary. If order is written, then we can assume it gives the maximum number of children per node. Similarly, degree gives minimum number of children. If the statement are quoted like this, a B tree with minimum degree 2, a B tree with minimum degree 4, minimum word is written or not, degree reflects minimum word. This means if in question order is given, you can assume maximum. In a question degree is given, you can assume minimum. And these two formulas given. I am just quoting the statement. Suppose the question is given, order a B tree of order 9. That means maximum number of children per node can be 9. And there is also a minimum bound. The minimum bound is ceiling value of maximum divided by 2, means 5. That means in this given question, each node can have minimum 5 children. 1, 2, 3, 4, 5. And this automatically reflects in this given statement, the minimum number of keys are 4. All keys less than 90 reside here. 90, 110, 150, 160. Between 90 and 110, all reside here. Between 110 and 50, all there. Between 150 and 160, all there. And more than 160 will reside there. I'm just repeating my statement. Suppose order is given, then maximum number of children is 9. To calculate minimum number of children, we use the ceiling value and maximum divided by 2. Suppose maximum number of children given 8, then it is 4. Suppose maximum number of children given 10, then it automatically computes to be 5. Number of children is 5, then number of keys are 4. Number of children are 4, then number of keys are 3. Now I am coming to degree. Degree is usually used more than order in your exam and in your concern. Degree means minimum. So the question looks like this. A B tree of degree 2. That means minimum number of children is 2. Minimum number of children means only one key. One child, another child. And maximum number of children is minimum into 2. That means 4 children. 1, 2, 3, 4. Automatically it computes 3 keys. So both formula are evaluated from each other. Suppose keys are given, then number of children can be computed. Number of children are given, then keys can be computed. Suppose in any example, you have given there are 5 keys. अगर 5 की है तो इसके 6 चिल्ड्रन होंगे. Reverse. Suppose in any example number of children are given 7, इसका मतलब 6 की है इसमें। तो ये तो सबसे पहले क्वेश्चन और उससे रिलेटेड एम्बिग्यूटी। नाउ आई एम कमिंग टू द practical problem. There are so many keys, but I will take only few of them. The question will be given like this: construct a B tree or insert following keys in the given sequence in an empty B tree. Empty B tree means only root node pointer with no key values. So inserting keys one by one, I will explain you the procedure. It will directly help you to solve the problem in a university exam and any other exam without going into so much technical definition and description. Picking the first value 162, and with this example the question will contain like this. The question statement will be printed like or quoted like this: insert following keys in an empty B tree with degree 3, with degree 4, with degree 5, suppose with degree 3, means degree is given 3. We automatically compute the minimum and maximum bound of each node. The minimum degree is 3, means minimum number of children are 3, yani minimum number of keys are 2. Keys are 2, children are 3. Similarly, maximum into 2 means 6. Maximum number of children are 6, then maximum number of keys are 5. It means each node will contain the space for storing 5 key values. Now, to save space, we can construct simpler, but it is my suggestion. You will construct with maximum occupancy. You will construct a node with pen and paper with maximum occupancy. So the maximum occupancy is number of keys are 5. So I will show you by drawing a single node 1, 2, 3, 4 and 5. This node reflects a storing capacity of 5 key values. Now, insertion having underlined process of keeping search property unviolated. First pick the 162. There are no keys here. Now, insert 162 here. Insert 162 here. Now, coming to second value 194. 194 will come compared with this. 194 is more than 162. It will occupy the next position, next empty position. Next, coming to 136. 136 will appear here. It will compared with 162. 136 is less than 162. So it is supposed to be reside here, means left of 162. So we will little juggle this. The first value is 136, the second value is 162 and the third value is 194. This will keep the search property not violated. Increasing order of keys value. Next is 188. Again the same logic. 188 will arrive here. 188 is compared with 136. It is more than 136. Then it will compared with 162. It is also more than 162. Then it will compared with 194. It is less than 194. Means conceptually it will reside between 162 and 194. So there is little movement. Here it becomes 188, then 194. Now, The next key value is 110. Again the same logic. 110 is compared with here 136. It is less than 136. So, the first value is 110, the second value is 136, the third value is 162, the fourth value is 188, and the fifth value is 194. Now the next 166. Now 166 will arrive. It is compared with 110 more than, 136 more than, 162 more than, 188 more, less than. Means conceptually 166 will reside in between 162 and 188. But there is no space, because for the given problem the maximum number of keys are given 5 in the same problem. The degree is 3, the maximum number of children are 6, then the maximum number of keys are 5. Means the node is full. That's why I have suggested you to make a node with full occupancy. It will reduce the error. Now the process of insertion. This single node is complete, full. For inserting a new value, it will split into two similar nodes. It will split into two similar nodes. Means now in place of one single node, two equivalent nodes are created. I am just coming to it. One, two, three, four, 5. 1, 2, 3, 4, 5. I have quoted the similar node. Means these all nodes are similar to previous one, having maximum occupancy pictured here, that is 5. 5 की वैल्यू रखने के लिए इसको हमने बनाया है. नाउ द प्रोसेस इज, अगर यहां जगह होती तो 166 यहां होता, जो कि नहीं है. अगर यहां जगह होती तो 166 यहां होता, जो कि नहीं है. 166 के आने से, ड्यू टू द अराइवल ऑफ 166 and the node is complete, the node will split. Total number of keys are 6. This will split it into 3. The first lower 3 are stored here, 110, 136, 162. Next keys in same sequence, maintaining search property, means maintaining this increasing order, will stored here, 166, 188, 194. Now and one more step is left. Now after splitting and copying equal number of keys, both, you will promote either rightmost of the left node, that means 162, or leftmost of the right node, which is 166. I am just repeating my statement. After splitting and copying, you have to promote one key one level up. This key, this promoted key will be the rightmost key of left node or the leftmost key of right node. This is due to maintaining the search property. Now, usually I promote the rightmost key of left node. So, 162 will come here. 162 will come here. And this key value will disappear. 162 is here in this node. There is a pointer from here to here and there is a pointer from here to here. I am just recalling the previous. In this node, there is a single key value. That means with a single key value, only two children are possible. The first children means the left children or the left subtree will contain all keys less than this key value 162, and it is reflected also 110 and 136 are less than 162. And in the right child or right subtree, all keys are more than this given key value 162. That is 166, 188, 194. So, when a node is complete, then a new key is arrived. For that, for insertion, the node will be splitted. Two equivalent nodes are created and height of the tree will increase by 1. Now, I am coming to next. And the next value is 147. Again, little attention is required because now the height of tree is increased by 1 and there are two levels. This 147 will arrive compared with 162. It is less than 162 and also the left child pointer of 162 is not null now. Previously, when single node is there and we are inserting 162, 194, then I have traveled along the node. Due to the fact, in a single node, all the child pointers are nil. So basically in algorithm, suppose 162 is written here and 192 will arrive, it will also check the left pointer is nil or not. If left pointer exists, then it will not move in node. It will not move in sequential in node. It will find for right. Suppose 194 arrive here and right child pointer is there, it will go to right child pointer, and the same logic. Because when 147 arrives here, it is compared with 162, 147 is less than 162, then it will also check for the left child pointer. Because there is a left node, so left child pointer is not nil. Then it moved to left child. Now, 147 is compared with 110. It is more than 110. तो प्रिंसिपली यहां भी चेक होगा कि इसका राइट चाइल्ड पॉइंटर है या नहीं है. नहीं है तो ये कंपेयर होगा 136 से. 136 से कंपेयर हुआ, ये इससे भी ज्यादा है तो 136 के आगे का पॉइंटर चाइल्ड पॉइंटर चेक होगा. फॉर्चुनेटली ये भी नील है. क्यों? क्योंकि ये लीफ नोड पे है अभी. तो 146 यहां स्टोर हो जाए, 147 यहां स्टोर हो जाएगा. नाउ आई एम कमिंग टू 126. अगेन द सेम लॉजिक. 126 is compared with here. It is less than. Check for child pointer. It exists. Then come to 110, 136. It will in between 136 and 110. So this is 126. I will erase this one to 126. Then 136 and then 147. Five spaces are there. Now, next key is 91. It will arrive, compared, left child pointer is tested, 91 is less than 110. Then there is a shuffling. 110, 126, 136, 147. The node is full. The next value is 151. This value again arrived compared with 162. It is less than 162. So it will go to find the left child pointer. Left child pointer is also existing. Then it go to the left child. It is compared with 91 more than, go for child pointer nil. 110 more than, go for child pointer nil. 126, 136, 147. The next child pointer is also nil. So it will try to insert here. It will try to insert here, but there is no space because the node is full according to our given question, according to our given occupancy. So it will now again split, and three values 91, 110, 126 in left child, 136, 147 and 151 in right child promote the rightmost of left, and this will grow the B tree. Thank you.